线下线上的这个各位老师同学们啊，大家早上好。今天啊，我们很高兴邀请到这个普渡大学王富强教授。那么我首先呢，就是简单介绍一下王富强教授。王富强教授呢是普渡大学的这个教授，现在也是福州师范学院的这个教授。那么他是早先呢是毕业中国科学与技术大学。后来呢，到美国在哥伦比亚大学获得这个博士学位，是在1996年。随后呢，他是在这个劳伦兹伯克利实验室做这样的做博士后研究。那么随后就加入到这个普渡大学做 faculty。那么他在2010年呢，这个当选美国物理学会的会士。这个王富强教授呢，主要工作的这个高能核物理的这些实验以及一些相关的一些理论的一些工作。那么他是 Fuqiang 的合作组的成员，也是俄州核子中心 CNS， 也是俄罗斯尼卡 NPE 合作组的成员。那么他在这些国际的合作中呢，都做了很多重要的这些工作。那么近年来呢，他的一个研究的兴趣是关于手振磁场效应的一些研究。那么大家知道，这些年来啊，对高能重离子动荡这个领域啊，这个手振磁效应是一个非常活跃的这个方向。那么自从应该大概10几年前嘛，理论上提出来在重离子动荡里面可以寻找这个手振磁效应这种奇特的这种吸引的这种突破效应，那么也掀起了这个实验寻找的高潮。那么Fuqiang这些年来，特别是通过这个 Isobar 的这个碰撞呢，对这个手振磁场效应做了相当大的努力，来寻找这些手振反常效应。那么刚刚前面的话，这个也是在年初的 relativistic 上发了一篇非常长的文章，来关于这个介绍其他这个国际合作组关于这个手振磁场效应方面的这个寻找。那么今天呢，我们富强教授呢也会关于这个 topic 做一些深入的这个讲解。那么我们这个论坛呢是复旦大学核物理前沿开放论坛。那么这次是第30次讲坛。那么也是这个得到了这个复旦大学核科学与技术系核物理离子束应用教育部重点实验室以及国家自然科学基金委理论物理专款上海核物理理论研究中心的支持。那么也同时呢有这个 nuclear science 跟 Techniques 这个刊物以及核技术刊物这个协办。那么今天啊非常高兴，我们邀请到这个王富强教授呢，给我们来做这个第30次的这个开放讲坛。那么富强，你请吧。
好非常感谢一刚非常感谢你的介绍，也谢谢你的邀请非常高兴能给这个 seminar Now I was speaking English but because a lot of terminologies it's hard to use Chinese not familiar 但是在讲报告之前就是感谢复旦大学，感谢一刚，感谢赵杰郭亮他们虽然说不能in person 的给这个 seminar 希望不久的将来可以见面online seminar 也很好这是我会给2个 seminar， 这个是第一个另外第二个 seminar 是下个礼拜所以都是讲CME chiral magnetic effect so again thank you very much and I will start so my title is experimental searches for chiral magnetic effect and this is the first part and I will talk about Isobar collisions but I will not spend the entire seminar on Isobar collisions. So this is my outline. And I'm going to give a somewhat long introduction, pedagogical introduction. And I like to do that because I think it's important to remind ourselves about the physics and the importance of the physics and why we do this research. For what? So I will give an introduction, and hopefully I will finish it within half hour. But I will try to, and then I will give a very brief. It's rather brief about the observables that we use to measure the chiromagnetic effect, and then I will mention or discuss, but rather briefly, the background issue. And I assume that everyone is aware of background in the CME measurements, so I don't have to dwell on that. But really, the background issue is the 99.9% of the effort that people put on trying to nail down the real signal of CME, which is related to the to QCD symmetry breaking. The main part of the seminar is going to be on Isobar collisions. Now it's probably not the longest part, but I hope that I will give you a flavor of what I think what isobars are important. I will discuss briefly the expectations and what we observe from isobar collisions. And I will spend some time, a few slides on the byproducts from isobar collisions. Namely, we can use isobar collisions to measure symmetry energy and the nuclear structure of the isobar nuclei. I will give you a refined baseline. We are investigating further contamination in the signal, mainly non-flow effects. And in today's seminar, I'm going to just give you a number. I will not get into the details how we get this number. I will postpone that part to the next seminar, really kind of get into the details of non-flow and how we extract non-flow, how we study non-flow and the effect of non-flow on isobar collisions. And finally, summarize. I will start with our universe. And let me get rid of text on my screen. Okay, so our universe is really, really strange if you think about it. It started with Big Bang, presumably, with equal amount of matter and antimatter. And today we have only matter. There's no observable antimatter from the entire universe. I should say the observable part of the universe. We can create antiparticles, but there's no big chunk of antimatter anywhere in the universe. And that's very strange. And another strange thing is that we have only left-handed neutrinos and right-handed antineutrinos. We don't have the counterpart. We know that particles like electrons have left-handed electrons, right-handed electrons, quarks, but neutrinos have only one set, and that is very strange. So the question is really why and how. Right? So let me see. For matter-antimatter asymmetry, Sakharov three conditions. Right? You have to have baryon number violation. You have to have non-equilibrium, because if everything is equilibrium, and then I'm talking about early universe. If everything is equilibrium all the time, then you have, if you have matter overcoming antimatter, so to speak, then you have the reverse, antimatter overcoming matter. So on average, they will be the same. So it has to be an effect of non-equilibrium processes. And then third, you have to have CP violation. Now CP is a symmetry which, or transformation of CP is transforms matter into antimatter and vice versa. So CP violation would mean that the physical laws governing matter and the antimatter differ somewhat slightly. So CP violation, C charge conjugate turns matter into antimatter. So turns charge of a particle to the opposite sign. And this charge means electric charge, baryon charge, lepton charge, all those quantum numbers. And suppose you have baryon violation, and one particular process would be proton decay. Right? If you have C violation, would mean that your decay rate of a left-hand proton or antiproton decays into electrons and electrons plus photon, a left-handed particle, would be different from the decay rate of the left-handed antiparticle, and you have the right counterpart of the right-handed particle. That would be different from the decay rate of the left-handed antiparticle. I hear echo from my own voice. Do you hear an echo? That would be different from the decay rate of the left-handed antiparticle. Wang said yes, he heard echo. There might be some feedback. Maybe somebody's microphone is open. Or okay, I think it's better now. All right, okay. So, but C violation is not necessary give you matter-antimatter asymmetry, and this is because if they're unequal, but you could have this left bottom decay channel decay rate equals to this right top decay rate. And then if you add the left side together, the right side together, you still have the matter-antimatter symmetry. So you would not have difference. So you would have to have inequality between the left bottom and the right, the top right, and the left top and the right bottom. So, and that is CP violation. So you have to have P violation. You have to have P, so that's parity, and then the combination of C and P has to be violated. And therefore, now if you have all these four, then matter and antimatter would be different. Okay, so and really CP is a transformation between matter and antimatter, not a C alone, because C would be a transformation from left-handed matter and the left-handed antimatter, and also for right-handed. But actually, a left-handed matter particle and right-handed antiparticle is the matter-antimatter pair. And that's very important. So somehow our universe preferred matter over antimatter, and actually preferred left over right. Somehow something happened at the beginning of the universe that favored matter over antimatter, and therefore we are left with a small excess of matter now, and this is about 1 out of billion, so 1 baryon out of a billion photons, because matter and antimatter annihilation produce photons. Now I said left over right. It is really, really strange that weak interaction happens only between left-handed particles. Right-handed particles do not have the weak interaction. And that is very, very strange. And we don't really know why. I hope Fred says something more about it. But parity and CP are violated in the weak interaction, and we know this, very familiar with this. Madame Wu did this experiment, confirmed Li and Yang's hypothesis. Actually, I have two physical review papers here, and they were submitted on the same day. One by Madame Wu, the other one by Leon Lederman. And this is because, this is a fun story. That Li TD told Madame Wu that parity may not be conserved. So here are the experiments that you can do to either verify that or refute that. Madame Wu did that. That was a very difficult experiment. You have to polarize the cobalt-60 nuclei at lower temperature, and she had to use facilities in Washington, D.C. But they did it within several months. And Madame Wu told T.D. Lee, and I heard that firsthand, that she told T.D. Lee that she had it, and asked T.D. not to tell anybody, because they were finishing they were still trying to finalize the experiment and writing it up. TD was so excited, he leaked the news to Leon Lederman. And Leon Lederman, they were doing experiment, and they just need to modify the experiment quickly. And actually they got results and finalized their experiment before Madame Wu. But they had an agreement that Leon Lederman would not submit their paper before Madame Wu. So they submitted the paper together on the same time. So the paper was published on Physical Review back to back. So now the parity violation would mean that the decay electron angular distribution is asymmetric. If parity is conserved, then the distribution will be symmetric about the magnetic field, either along or anti-parallel to the magnetic field. And they observe only one direction. The electrons were emitted in one direction. And so that's a maximum parity violation. And the reason is that the parity refracted process of this decay would mean that you would have to have left-handed antineutrino. And since we don't have left-handed antineutrino, you just simply don't have this. And therefore, it's a maximum parity violation. Same for Leon Lederman's experiment. It's a pion decay into muons. And because you don't have you have only one side of the neutrinos, the other side just does not happen in our universe. But if you do CP transformation, then that's allowed. So that decay, pion decay, is CP conserved. It's a weak decay, but it's parity violated, but CP conserved. We do know that CP is violated too in the weak interaction. And this is due to the electroweak symmetry breaking, the Higgs mechanism, basically. That's how quarks get masses. And the flavor eigenstates and the mass eigenstates are not the same. And this mixing gave you the CP violation. And that's the familiar CKM matrix. That's so Kobayashi and Masukawa got Nobel Prize for this, not Kabibo, but so they got half of that prize, and the other half went to Nambu. So they demonstrated that you cannot get rid of the. So by transformation, sometimes you can get rid of the phase angle, right? But they demonstrate that the CP phase angle cannot be got rid of if you have 3 generations of quarks. If you had only 2 generations, then they can get rid of. So the phase angle is not meaningful. It's not physically meaningful. So that's again. We know that we have CP violation measured in K long, K short decays. So that tells us that we must have 3 generations of quarks, or at least 3, and that's so that's why the top quark was not a Nobel Prize, right? Because that was known that top quarks must be there. It was discovered in 1995, long after. That's all good, but the CP violation in weak interaction is not enough. So the violation strength is proportional to the 3 flavor mixing angles and the CP violation phase angle, and the differences between the mass squares of the quarks. Now to get a dimensionless quantity, you have to have a temperature, and the only temperature scale or only energy scale is the electric weak symmetry breaking temperature on the order of 100 GeV. If you plug that in, you get the baryon antibaryon asymmetry of 10 to the minus 20 power, and that's far smaller than 1 out of a billion, 1 baryon out of a billion photons. So that tells us that weak interaction is not enough, and that's why I said that the CP violation responsible for matter antimatter asymmetry must have happened very early on in the early universe, not later due to weak interactions. So therefore, there must be something else, and the something else is the CP violation in the strong interaction. We all know that everything is conserved in the strong interaction, and that is very strange because weak interactions, strong interactions are really both are non-abelian, and therefore all those symmetries should be violated. There's no reason to expect the violation to be different in strong interaction. So you would expect the CP violation in the strong interaction to be, say 1% or maybe 0.1%. That's my way of thinking. I don't really know this number. I guess nobody really knows, but I would not be surprised that the CP violation in the strong interaction is on that order. And this is not new, right? People knew this long time ago that the parity is violated in the strong interaction. It's not directly observed, but this is the chiral anomaly. That is that classically. So first of all, again, QCD is a non-abelian chiral gauge theory. It really deals with chirality. So that's the Lagrangian here, and so quarks, gluons, quark-gluon interaction, gluon density, and so on. And if you look into this in detail, the interaction happens only between left-handed quarks and right-handed quarks between themselves, but not between left and right. The interaction between left and right only through the mass, or the mass is rather the manifestation of this symmetry breaking. But the light quark mass is really small, so that's not a big part. So it's really kind of 2 worlds, left and right. And classically, you would expect left and right to be conserved individually. So the number of left-handed quarks and number of right-handed quarks are both conserved, and they don't talk to each other. But quantum mechanically, you have to do higher order corrections, and the first correction would be this triangle diagram. And this is called, and because of this triangle diagram, it is found that you cannot have both quantities to be conserved. And it turns out that the total, the so-called vector current is conserved. The total number of left-handed and right-handed quarks is conserved, but the difference is not conserved. So that's called the chiral axial density non-conservation. And this is a problem. This is called the UL1 problem in the 70s. This was, so this was not directly observed, but it was proven that this is needed in order to explain experimental observations, like the big difference of the masses between the eta and the eta prime mesons, and the pi zero decay constant, because the pi zero decay constant calculation requires a triangle anomaly, something like that. It's not this one, but another triangle. So this was proven to be correct, and the question is how. And then comes T. Hooft in the 90s. I think he did this in the 80s, and he in the 70s, excuse me, middle 70s, just a few years after the UL1 problem. And he pointed out that in the Lagrangian, there should be another term, and this term is the Gruon pseudoscalar density. And effectively, it is the dot product of the electric field, the color electric field and the color magnetic field. And this term is really the dot product of E dot E and B dot B. That's the energy density, which is E squared plus B squared, but that's not a Hamiltonian, this is Lagrangian. So it's E squared minus B squared. So this term is called, this is a vacuum, it's called the theta vacuum term, and it explicitly violates CP symmetry because of the electric field and magnetic field. The way I look at this is that this is chiral, about a chiral. It's not a helicity, but I like to look at this in terms of helicity. It is really like, you have magnetic field, you have a left-handed quark. If you put it into an electric field parallel to the magnetic field, the momentum will flip, it'll become a right-handed quark. So now you have a change in the handedness. Now, I know this is wrong. It's a good way to look at it, but it's not what's going on here. This is about the chirality change, not the helicity change. So anyway, this quantity is called topological charge. It is a quantum number, and quarks interacting with this Gruon field would change chirality, and therefore the difference between right and left is not conserved. It's changing, and the amount of change is characterized or is quantified by this topological charge. Okay, everything is beautiful except that we don't observe it. So that's called the strong CP problem. You expect CP is valid in the strong interaction, but you don't observe it. From the neutron electric dipole moment measurement, the theta term is zero, basically. Theta is zero. Theta has to be practically zero. And this is, the theta is an angle. And so this is the so-called fine tuning of the universe. And that's very unnatural. So that prompted Percy and Quinn to come up with the axion field. So they come up with the axion, so-called UL1 symmetry Fuqiang Percy Quinn PQ UL1 symmetry. So they promoted this into a field basically, and so it's just like the way I think. I'm not expert. The way I'm thinking of it is that it's somewhat like the Higgs field. So it's so you have this field, and the field is somewhat, you have this symmetry, and this symmetry is simultaneously broken, and therefore it takes on a vacuum expectation value, which is non-zero, and they say that this expectation value is the theta term. So therefore, if you take the A minus the expectation value as the physical axiom, then this expectation value is the theta term. So the theta term cancels. So you are left with no CP violating theta terms in the Lagrangian. But you have an axion field, just like the gluon field, the photon field. You will have to have extra terms in the Lagrangian to include the axions. It's not observed so far after 40, 50 years, but still it's a very attractive solution. So the theta vacuum is topological, and because you have these quantum numbers, so corresponding to different quantum states of the vacuum, and they don't talk to each other. The probability of the tunneling probability is very small, and since this energy barrier is very high at not at a very high temperature, you would not have crosstalk between the vacuum states. But the physical vacuum has to be a superposition of the quantum vacuum states, and therefore you can have vacuum fluctuations, and you can have local regions of domains with non-zero topological charge. So it's all about left-right. So this is kind of my understanding about the symmetry breaking. We have the electroweak symmetry breaking. That's the Higgs mechanism. Basically, a left-handed particle, fermion, interact with the Higgs field, turns into a right-handed fermion. So, for example, a left-handed quark becomes a right-handed quark, and through this, the quark gains mass. Before that, before electroweak symmetry breaking, all particles are massless. And actually, the way I look at it is that actually the left-handed, for example, the left-handed electron and the right-handed electron are actually two different particles. We call them electrons, but they are different. They are two different particles. And the positrons you have left and right, they are two different particles. So actually you have four particles, and that's the Dirac's equations, right? You have the two spinors. So it is really two different particles. So you have actually four different particles here. It happens to be that the right-handed particles do not participate in the weak interaction, and that causes all those symmetry breaking issues in the weak interaction. Now, I should mention about the neutrinos. We know the neutrinos have some mass. That means that the neutrino, we have left-handed neutrinos only, but they must have, if they have mass, then you must have a right-handed neutrino. And the way people think about this is that the right-handed neutrino is so massive, it has decayed, and there's no right-handed neutrino left in the current universe. But yeah, that's my speculation, and and that's a very active research in terms of neutrinos, right? So nobody really knows what's going on. I talk about the UL1 symmetry breaking. It's I said temperature 1 GeV, but I don't really know. It could be the same as the chiral symmetry breaking temperature, a few 200 MeV. So this is the topological charge, the chiral anomaly. It's purely quantum mechanical. When the temperature is lower, then now you form chiral condensates. You have left-handed quarks, right-handed antiquarks. Also, left-handed, right-handed quark antiquark pair, and they condense, and that they sit in the vacuum. You have now you have so the chiral symmetry is simultaneously broken in the following way: that if you have now a left-hand quark come in, interact with the vacuum, and the left-handed quark has to interact with left-handed antiquark, because the left-handed quark does not talk to the right-handed quark, only through the mass, but the mass is too small. So now they are gone, and you're left with the right-handed quark. So it appears that you started with a left-handed quark, and then you end up with a right-handed quark. So you have the chiral symmetry breaking simultaneously, or spontaneously, excuse me. And through this, you gain mass. So the mass is due to the condensate. And that's the 99% of the mass of the product. So that's all about symmetry breaking. And we have, theoretically, we have this nice UL1 symmetry breaking in the strong interaction. And how do we observe it? And that comes to the chiral magnetic effect. And I think I can go quickly. If you have a domain with non-zero topological charge, then you can have unequal left-handed quarks, right-handed quarks. They're still random. You have to put them into magnetic field to line up the spins, and therefore you have suppression. Of course, you have the majority of the quarks are still, in terms of charge, random up and down. And what matters is really the 4 right-handed quarks, because you have a topological charge of 4 domain. And they will, because of the charge, the magnetic moments depends on charge. So you have a charge suppression along the magnetic field. How strong a magnetic field do you need? Well, you need a magnetic field strong enough that the quarks are really aligned with the magnetic field. So the energy due to the magnetic field, mu dot B, has to be a lot bigger than the thermal momentum, right? Because otherwise it will be still randomized. So that's the Lono energy level. And so I basically say I need 1 GeV. So that's much bigger than the thermal temperature. So that's safe enough. That would mean that a magnetic field of 10 to the 13 Tesla. A way to convert from natural units to Tesla is really a pain. But at least every experimentalist knows this pocket formula. P equals to 0.3 BR in terms of units, GeV, Tesla, and meter. And that's why if you are in STAR, you know that our acceptance cutoff is 150 MeV, because our TPC is 2 meter in radius. So this radius has to be 1, the circle within half of the TPC. Magnetic field half Tesla, so that's 150 MeV. That's the cutoff. So this turns out to be 10 to the minus 9 MeV square, and that would mean 10 to the it's about the pion mass square. We do have a very strong magnetic field, 10 to the 15th power. That's a back of envelope calculation. Model calculation is not far off, only 1 order of magnitude off. So the magnetic field is really strong. The problem is that it may die off quickly. Now the hope is that we have this QGP with good conductivity, so the magnetic field is trapped, so it does not die as quickly as in vacuum. And if we have a strong magnetic field lasted for a long time, then we have hope to observe the chiral magnetic effect. So this is just a comparison. I don't know how much CP violation in the strong interaction is needed to explain the 1 out of billion matter-antimatter asymmetry. Because I so far has talked about left-right parity violation in the strong interaction. Now that topological charge term, the theta vacuum, is explicitly CP asymmetric. So there ought to be CP violation, but I don't have a good feel. But I asked Jinfeng about, so Jinfeng has an estimate from Glasma. And he had an estimate of the axial current density per entropy density on the order of 10%. And this would be, if nothing, my understanding is that this would be your asymmetry, the charge separation asymmetry that you measure. But of course, we have heavy ion collisions, we have evolution, we have a lot of final state interaction. And Guoliang showed many years ago that this effect is a factor of 10 reduction. So the final state effect dilute, so destroys the initial charge suppression by a factor of 10 or more. So this 10% becomes 1%. If it's 1%, we can observe it. If it's 0.1%, there's no hope. So it really depends on the magnitude. And of course, my guess is that nobody really knows how big a CP violation in strong interaction is needed to explain the matter-antimatter asymmetry. And therefore, we have to answer this experimentally. So that's a recap. I will skip. So we have to recreate the early universe to observe, hopefully to observe the chiromagnetic effect. We are looking for this charge suppression, and this is the variable we use. And this is from Sige almost 20 years ago. This was the first measurement, as most of you know, if not all of you know. We did observe a very strong signal, 10 to the minus 4, or a few times 10 to the minus 4. And that means a few percent, this axial current, or A1 a few percent. If there's a reduction of factor of 10, then that it would mean a few 10% CP violation to start with. We had a press release. It was too early, premature, because there is a big background. And actually, Sige realized that in his seminal paper in 2004 that there is this background. But actually, it was not realized that the background is very big. And actually, so the background is really due to, cluster, also like a row decay into pions. So the signal is back-to-back, perpendicular to the reaction plane, and the background is those pairs in the same direction along the reaction plane. In terms of this observable, the CME pair and the decay pairs are identical. This observable will give you the same number, same value. And we have this background because we have more row in the X direction, in the impact from direction. Therefore, you have more such pairs, and therefore you have the right sign in terms of a background mimicking the CME. Mathematical or algebraically, you have this background being proportional to the V2 of the residences or clusters, being proportional to the angular correlation of the decay, being proportional to the number of clusters, and of course, only proportional to the number of pairs, because we form pairs to calculate the average per pair. So at the end of the day, it's proportional to V2 divided by N multiplicity. Okay. Theoretical studies, model studies indicate that actually the background can explain 100% of the observed signal. Back of envelope calculation, you have 20% or low over pion ratio of 20%, medium central collision 100 pions, flow of 10%. You get to the order of 10 to the minus 4. So the background is really measured, and therefore, whatever you measure is contaminated by background to a large degree, majority. Then then you can't really rely on models or theoretical calculations or anything. You have to measure it. So I will skip this one. I will say something more during the next seminar because I'm kind of running out of time. But this slide is just a compilation of all results confirming that background is really large. So you really have to nail down the background experimentally. And the best way to do that is to cancel the background. So you devise your experiment, your apparatus, or your whatever way you do. You want to do measurements and compare the measurements. You want to do comparative measurements. And between these two measurements, you have a very good control of background, and therefore they can be canceled. And then what's left is the signal. So that's the idea of Isobar collisions. This was proposed by Sigi in 2010. So we have ruthenium and zirconium. They have the same number of nucleons. So you expect the background to be the same, and they differ by the number of protons by 10%. So therefore you expect the signal or CME correlation signal to be 20% different because it's B to the square, or it's really, we're measuring A1 square. Model calculations tells us that it's about 15% difference. This is estimate from Fuqiang and the company about the signal background ratio estimates as a function of the background level in your inclusive measurement. And this is the significance here. Since we have more data than the statistics that they used, so this significance number should be multiplied by square root of 5 according to our statistics. So you see that if the signal is 10% or background is 90%, then you get a significance of 1.5 times square root of 5. So you get a 4 sigma effect. That's a very good signal that you could measure. You can estimate this with on the back of envelope easily because this is the angular correlation. So the width of cosine angle distribution plus minus 1 would be 2 divided by square root 12 divided by number of pairs, square root, additional square root of 2 because you take difference between OS and SS, and so on. You get the error on the delta gamma to be 10 to the minus 6. We do know that the delta gamma average from Isobar is about 10 to the minus 4, 3 times 10 to the minus 4. So there's additional factor of 2, square root 2, because you have two systems. The estimate would be 0.4 statistical precision. If the signal is 10%, or CME is 10%, we are measuring 15% difference. So we should be measuring 1.5% difference. And 1.5% with 0.4%, that's a 4 sigma effect. So this is very hopeful. Until that, and this is really bothered me personally, because we were using AVFD simulation. So we try to do simulation to mimic data. So this is to prepare our brine analysis. So we generate simulation data and we try to look at simulation data through a brine analysis and to make sure that we have everything thought through, everything is correct. And I was, and Jay knows this, that we were looking at this and we were so confused or puzzled, but only for a brief moment, actually, because we saw something really, really strange, that we saw something that we did not expect. but only after a few minutes, we realized that this must be correct. And this is something that we should have thought of a long time ago. This is just very, very trivial. That is that because isobar is smaller, you produce fewer particles. Background is inversely proportional to multiplicity. Therefore, you get factor of 2 higher background in isobar than in gold-to-gold collisions. The signal in gold-to-gold is bigger because the magnetic field is slightly bigger. So that's a factor of 1.5. So you're talking about a factor of 3 difference in the signal over background ratio between gold-to-gold and isobar. The reason that we picked 10% in our BUR and in Xiguang's publication, they used 1/3. They were more optimistic, but we picked 10%, and we thought that was a good ballpark number because we had a feeling that if there was signal, it's probably on the 10% level. Okay, and that's from the gold experience. But if there's really a factor of 3 reduction in the signal, we're talking about 3% in isobar, and 4 sigma becomes 1.3 sigma or 1 sigma, and that's hopeless. That's hopeless. So this is really something that dawned on me, actually surprised many people actually that we did not thought of this way before. So anyway, this is the data. So we measure delta gamma over V2 ratio between the 2 systems. We did achieve 0.4% precision. We have several groups. All groups agree. And the strange thing is that the ratio is below 1, while you expect something above 1 if there is CME. And we quickly realized that there's a multiplicity difference, right? And I knew that long ago, so I was not surprised. So it's inversely proportional multiplicity, and there's a big difference in the multiplicity, 4.4% difference, a huge difference between these 2 isobar that you thought would be identical. If you invert the multiplicity, you see the shape is identical. And this shape is, I mean, this wiggle shape is an artifact of our centrality definition. Right? We define centrality in such a way that it's 5%, 10%, and so forth. But it's not exactly 5%, 10% because multiplicities are integers. So there's this artifact that's well understood. The beta variable would be multiplicity times delta gamma over V2. We had only analyzed the delta gamma over V2, and that's why the ratio is below 1. If we had the multiplicity in there, then it'll be above 1, and that will be a couple of slides later. Let me just get to the nuclear structure. The isobars are not identical, and we actually predict that. Using density functional theory calculation, putting in the nuclear interactions, and you can predict the structure, the density, the proton and the neutron density distributions. And it's no surprise that the zirconium would have a very thick neutron skin because it has more neutrons. And as a result, the overall size of zirconium is bigger. And therefore now zirconium collision has a bigger volume with the same energy. So your energy density is smaller, and therefore your multiplicity is smaller. And this difference is 4.4%. And we actually predict the shape quantitatively. And this is the measurement is these gray points, and the red histogram is calculation. The red being the one would be something similar to the top plot. Okay. Besides the multiplicity, the V2 is different. And this is because if you have different size, if you have hard sphere, smaller size and a bigger size, the eccentricities will be different. This was really a surprising. And several years ago, actually, I reviewed a paper from I won't say, but it's they actually studied this and actually using Huddersfield, and actually the size matters for eccentricity. It turns out that a smaller size would give you a bigger eccentricity, and the difference is 2 to 3%, and we predicted that almost semi-quantitatively. Furthermore, actually, we predict the V2 difference between the two systems with respect to the impact parameter is 10% different. And that's actually what measured, almost 10%. So these nuclear structure calculations is really trustworthy, that you get almost everything that you measured. And actually this tells you that that the impact parameter or the spectator plane and the participant plane, they are different, of course, because of fluctuations. And the average angle, opening angle between these two planes are different between these two systems. And that actually motivated or stimulated our thinking of the spectator plane, participant plane method to measure CME, and that will be something that I will discuss next week. But anyway, I'm running out of time, so this is the money plot of Isobar collisions, if everything is inversely proportional to multiplicity, the baseline should be this lower dashed line, and you see that all the data points, the black data points, are the delta gamma ratios. All those black points are above that line, a few sigma. Okay, so if the baseline is this lower dashed line, we got a signal of 3 sigma CME, and that's actually what Dima and Jingfen and Suze pointed out, that actually if that's the baseline, we got a signal, a few percent. Now, of course, this is inversely proportional to multiplicity is only an approximation. It should be proportional to the number of clusters divided by the number of pairs. And if your cluster multiplicity is not proportional to multiplicity, or there is slight difference between the two systems, then you're going to have some effect. And that's actually captured in this quantity we call the R variable, the R ratio. And that is really the difference between unlike sign minus like sign, the excess of these unlike sign pairs, and the difference in this quantity between the two isobar collisions is this upper dashed line, and the data points are between these two dashed lines. But we can do better. The additional, those baselines are really naive expectations, and in our measurements there is non-flow correlation, and those non-flow affect numerically our measurement, and we can estimate those non-flows. And I'm not going to get into details. I will do that next week. But with all those non-flow estimate and intrinsic 3-particle correlation estimate from hygiene, now we get this baseline, refined baseline, which are shown in those shaded area. Okay, so the average and the band or the area width is the uncertainty. The middle would be the nominal value, and the nominal value is somewhere in between these two dashed lines. And right now the bands are consistent with the data points, meaning that the measurements are consistent with all background. And if I estimate an upper limit, So the error bar right now, say 0.4 from data, 0.3 and 0.5 from the baseline estimate. You get an error of 0.7%. And this is about 5% CME, 1 sigma. So therefore, if we measure 0, our upper limit now is 10% at the 98% confidence level. Upper limit of 10% CME in isobar collisions. And we are improving our estimates, and I can tell you that the error bars will be shrinked. I cannot tell you the number. We are going to publish it in a few months, hopefully. And so we will have a more stringent upper limit than the 10%. With that, I don't know how much time I can run over, maybe 2-3 minutes, and then I will conclude. So I want to talk about the byproducts. So I told you that the nuclear structure calculation is quite trustworthy, and you can actually measure the neutron skin from isobar collisions through by the difference in the multiplicities and so forth. And the neutron skins are sensitive to the symmetry energy. So you can actually measure symmetry energy. I'm not going to talk about details, but the neutron skin is linearly correlated with the slope parameter of the symmetry energy. And this slope parameter is very important because this tells you, characterize how the symmetry energy, which is due to the asymmetry between protons and neutrons in the nucleus, vary with your nuclear density. And therefore, it has a direct consequence or relevance to neutron stars and the equation of state at the higher density. We can actually measure this using high energy nuclear collisions. And that's something that is mind-boggling. But I think that there's no flaw there, and I think it's really true that we can do that. These are the preliminary data from STAR, and we measured the L parameter from isobar collisions, and we put it together with WARD data. And as you can see, the pink data points are from STAR measurements using high energy collisions. And it's consistent with all other data from low energy nuclear collisions, nuclear reactions. And the error bar is comparable, better than some of the measurements. And we are consistent with WARD data. And actually, there was a big anxiety or excitement about the PREX2 measurement being higher, although only by less than 1 sigma from the average WARD data. But the statistic is really not enough from PREX2. So anyway, all I'm saying here is that we can contribute to that enterprise from nuclear collisions at high energies. I will skip this one. We published a letter, a PRC letter, by proposing to look at very peripheral collisions, because that's where the neutron skin is, and therefore it's most sensitive to the neutron skin, and therefore you're most sensitive to the symmetry energy. The downside is that the statistics of those peripheral collisions is low. You don't have many of them. And we have a question or a puzzle that I don't understand yet. Our data is very, very different from Pythia prediction, because these are very peripheral collisions. It's a very simple superposition of nuclear collisions. You can predict that from Pythia, and it's very different from data. So something is strange here. I'm very confident that our data is correct. So there might be something there that is not uncovered yet. So come to my conclusion. I don't have to repeat how important the CME is. It's really, we're really dealing with or investigating or studying or discovering the basic fundamental symmetry in QCD or in nature in our universe. Isobars have been very, very powerful, but nature is not kind in this case, that the signal is weak and the data are not enough to make a decisive conclusion. Next week, I will talk a little bit more about Isobar, and then I will tell you more about the gold-to-gold collision, and I think there is hope in gold-to-gold collisions. So at least I'm not going to give out the conclusion, but I can tell you that I'm more optimistic than before. So thank you very much, and sorry for running over the time.